In Symmetries and Particles and Fields, Lecture 20, we begin a new chapter, Chapter 8, on gauge theories. This is going to come in three parts. We begin with a run-up problem on abelian gauge theories. Then we'll generalize to general groups, where the matter transforms in the fundamental representation of the general group. And then at the end, we'll show how this changes when you have matter in general representations. For this lecture, though, we'll stick to U1 gauge theory. That's the abelian version. And we see how making the phase change depend on space and time requires the introduction of a new field in order to get invariance. And this new field is going to be a massless spin one interacting boson, just like the photon is. So actually, we can make a theory of scalar quantum electrodynamics this way. And we're going to do that now. All right. Section 8, gauge theories. So let's take the theory of a complex scalar, phi. And it's got some charge Q under a U1 transformation. So Q is an integer under, well, it better not be zero, actually. So this scalar field, this complex scalar, goes to e to the I eq alpha times phi. Now, I put some additional symbols here, and we'll talk about those in a second. But this implies that phi dagger goes to e to the minus I eq alpha phi dagger. So the idea here is that alpha is between 0 and 2 pi. This is the angle, the group parameter. It's the angle of the phase. And previously, we haven't separated out EQ and alpha. We've just put them all as one thing, alpha. But EQ and alpha are going to acquire different meanings. As I said, Q is this charge. Alpha now is between 0 and 2 pi. And E will take the role of a coupling constant. It's a real number. And if we increase it, then some interactions that we're going to derive this lecture will increase in strength. Now, hopefully you know from constructing Lagrangians in quantum field theory that the following four-dimensional Lagrangian, where phi is some four-dimensional potential, this is invariant under the U1 symmetry. So, okay, up to now, we've only considered global transformations. So alpha is a constant throughout all of space-time. transformations of internal symmetries. So these have been independent of x mu. But what happens if we try to put alpha is a function of x mu? So I've just indicated it by alpha of x here. So in other words, we're allowed to rotate the field differently at different space-time points. Well, okay, so when we do that, we see that phi dagger phi is still invariant. So the potential is V, which is a function of phi dagger phi, is as well. But the problem we have is with this kinetic term, because now this d mu is going to hit the alpha, which depends on space-time in the transformed field. So this first term here is the kinetic term. And the kinetic term isn't invariant any longer. Because the d mu hits the alpha mu. Sorry, the alpha, which is a function of x. So there's a little exercise for you at this point. As I'll do it now. Find the change in Lagrangian, and you should get a non-zero change if alpha is a function of mu, a function of x, and you don't change anything else about this Lagrangian density. All right, so you'll find that it's non-zero. And so to reassert the invariance under this new symmetry, which is now space-time dependent, we have to add a new field. So to reassert invariance, we add a new field. And this field's called a gauge field. I'm going to call it A mu of x. It's a quantum field. So it has creation and annihilation operators inside it, in some integral with some Fourier terms, e to the ip dot x, etc. And we defined a new object. Instead of this partial derivative with respect to x mu, we define what's called a gauge covariant derivative, which is slightly modified. So on the next page, we're going to just define that gauge covariant derivative. So instead of partial d mu phi, we're going to define this gauge covariant derivative d mu phi. Oh, sorry. I should have said, really, this is a gauge covariant derivative of phi, big d mu phi. So this is defined to be, well, it's the partial one minus IEQ A mu phi. Okay. And now we're going to change the gauge transformation. We're going to let phi, both of the quantum fields that we have now, both phi and this A mu, we're going to let them transform simultaneously under a gauge transformation. So these are now, because alpha depends on x, these are called gauge transformations. So phi of x goes to the same thing that it did before, but at the same time as transforming phi of x, we transform this field A mu of x as well. And what we do is we add some partial derivative of alpha onto A mu of x. And the reason we do this is, of course, is because it's possible to change our original Lagrangian, but into a form that's gauge invariant, that's invariant under these transformations. So we define a new gauge invariant Lagrangian density, which will be the one that we use for these kind of theories. L. Oh, okay. I'll show you that in a second. But to firstly, let's just see how this covariant derivative transforms. So first note, this is going to basically make the algebra simpler, so it's worth it. After all, we're all lazy. We don't want to do too much algebra. Some more room for mistakes then, which, if you're me, happens a lot. Okay. So we just substitute in in for d mu phi, because we've defined it on the top. But phi and a mu now transform. So we have to take both of those things into account. Okay, so well, we get two terms from this first bracket because the partial derivative acts on the alpha and then it acts on by the chain rule on the phi. So I have to put the x dependence in there to remind ourselves. So this is multiplied by. So when it acts on the alpha, we get IEQ d mu alpha times e to the I EQ alpha phi plus e to the I EQ alpha d mu phi. All right, and then we have minus I EQ a mu e to the I. Sorry, this should be EQ alpha in the exponent there. E to the I EQ alpha phi minus I EQ d mu alpha e to the I EQ alpha phi. And what we get is that the first and the last term cancel. All right, so we can realize that we can rewrite this these two terms in terms of the covariant derivative, and this is just the e to the I eq alpha d mu phi. Okay, so we know how d mu phi, all Hermitian conjugated transforms. We just get e to the minus I eq alpha d mu phi dagger. You can check this by expanding it all out if you wish. So what we see then is we see how to write down a new kinetic term. If we just multiply d mu phi, the covariant derivative, by its Hermitian conjugate, then these factors, these phase factors in front will cancel. So a new kinetic term d mu phi dagger d mu phi is then invariant under the gauge symmetry. So this new field that we've had to necessarily introduce is the photon field, or it's a spin 1 massless gauge boson. So if we make this U1 electromagnetism, then it's actually the photon. In fact, we're going to need this to be a propagating field because we want to model electromagnetism, in fact. So it needs its own kinetic terms. Otherwise, it won't propagate. So these kinetic terms are written in terms of what's known as a field strength tensor. Typically denoted F mu nu, and it's defined to be d mu a nu minus d nu a mu. All right, so we'll see now how to, in just a second, how to construct the kinetic terms in the Lagrangian density for this photon field. But let's consider first how this F mu nu transforms under the gauge transformation. We know what it is in terms of partial derivatives in the photon field, but we know how the photon field transforms as well, so we can work that out. So F mu nu goes to d mu of a nu plus d nu alpha minus d nu of a mu plus d mu alpha of x. Okay, so what happens is that these two terms cancel and we just get that F mu nu is invariant. Under the U1. So we're ready to construct our full U1 gauge invariant Lagrangian now. Lagrangian density, Lagrangian. So I'm going to call this scalar QED. So this is minus 1/4 So F mu nu on its own is invariant, but this has mass dimensions 2. We want something of mass dimensions 4, and furthermore, we need to soak up these Lorentz indices. Remember, they need to be summed over, otherwise the term won't be Lorentz invariant. So if we want a Lorentz invariant quantum field theory, we need to sum over them, and that's the correct way of doing that, given that mu and nu are antisymmetric. Plus d mu phi dagger d mu phi minus some potential which depends on phi dagger phi. Okay, so here's our 4-dimensional U1 invariant Lagrangian. Now, maybe I'll just put the minus v here. All right, so these give us the photon. Photon's often written as gamma after gamma rays. Photon gamma kinetic term. So although the field is written with an a mu, when you're talking about a particle, you denote, in terms of the photon, you denote it with a gamma. All right, so these terms here. So there are 4 terms here because remember, this is d mu phi dagger plus IEQ a mu phi dagger times d mu phi minus IEQ a mu times phi. So this gives you some terms, one of which is an ordinary kinetic term for a complex scalar, but it also gives you a q squared term, e squared q squared times a mu phi dagger phi. And there's another term, these kind of cross terms, where you get things like minus IEQ d mu phi dagger a mu phi. Now, it's beyond the scope of this book to give you what happens, how to construct Feynman rules out of these. But basically what you're looking for is the prefactor. So when you do the scattering computation, you've got some external states and you match those up with creation and annihilation operators within these fields in the Lagrangian, because we're doing an expansion in e to the I times the action. Okay, so what happens is we can take a creation or an annihilation operator from a photon in this field, one from a photon in this field. So this wavy line denotes a photon. The dashed lines denote these phi particles. And we get that the Feynman rule for this is proportional to the factor in the front. And actually we get a factor of I from expanding e to the I times the action. And we also get a factor of 2 because, well, if I give these different Lorentz indices, really what we've got is e to mu nu between the 2 photons. But I can basically link up, topologically, I can link up this photon to either that, an operator, annihilation operator, either in the first photon field or the second one. Okay, so this is what the Feynman rule looks like. So to calculate the scattering probability, we're allowed to draw diagrams that include these vertices, and whenever we do, we must include a factor like this. But for the second term, now this looks something more like the following. We have one photon field interacting with our phi, And the phi has charge, so it has, this is the direction of flow of charge. And what happens is, well, we get a factor of I, but there's a minus I in front, so that cancels the I. This goes like the prefactor, which is EQ. And what happens with this derivative is it pulls down I times a factor of the momentum of this photon. Okay, so we get I times the momentum of the photon. All right, so that's the Feynman rule for this vertex. Now, we could, if you've only got one complex field, like I was talking about, actually, I could just rescale this coupling E to absorb Q into it. Everywhere we see E, there's a Q next to it. So Q can be absorbed into the definition of this coupling constant. This coupling constant is just some real number that we fixed by measuring scattering cross sections, unless there are several fields. So if we've got several complex fields, phi I, with different charges, so charges qi, each of which is an integer, then under U1, what happens is that each of these phi i's transforms e to the I alpha I qi. So sorry, I should put it the other way around. Qi alpha I times phi I, no sum on I. Okay, and then we can, there's a straightforward generalization where we just put i's into this Lagrangian and actually sum over them, and the whole thing will be gauge invariant. So that's the reason I've separated out E and Q. Good. Now, it'll be useful, we're going to start non-abelian gauge theory in a second, and it's going to be useful for us just to notice something. There's a relationship between the covariant derivative to notice that the following commutator of d mu and d nu acting on phi, well, we know how to calculate this. Okay, this is these four terms minus mu switch, the same four terms minus mu switching with nu. Which is minus I EQ. So loads of the terms cancel, and we just end up with 2 at the end of the day. Of course, they're anti-symmetric in nu switching with nu. So the partial derivative here only acts on the a nu within this bracket now. So I can redefine this by substituting in the field strength tensor. Okay, so we're going to use this in the non-abelian case next lecture, I think. So the commutator between these two covariant derivatives just gives us something proportional to the field strength. Okay, so now let's go to non-abelian gauge theory. So that was our simpler case. So we're going to have the simplest thing to do is to put a scalar in the fundamental representation space. So we have a general gauge group. G, fixed to UN or some subgroup of it. So for example, we could have common ones you'll see at SUN. We could have products. So we could have semi-simple products. But actually, we're going to take, I don't know, let's just take a single simple group for now. It's a bit simpler. There's a trivial generalization to semi-simple groups. So let's just take that. Typically, you'll have things like this. So for a fundamental representation scalar, so for a complex scalar in the fundamental representation, so we have now phi. Well, there's going to be some n component vector, say. So for SUN and SON, of course, well, all right. So it's a complex scalar in the SUN case. It's a real scalar in the SON case. These details don't matter so much. So each one of these curly phi n's is a complex scalar field in the SUN case. All right, so let's take some global group now. So global group G, which we've been dealing with up until now. So the theory, remember, is invariant. Under our vector of fields goes to G times phi of X. Now, G is a member of our non-abelian group. So now let's allow these group transformations to depend on space and time. So now we require G of X to be within the group to depend on space-time. So an example would be the color symmetry. Let's say I want to transform red quarks into blue ones in India and red quarks into green ones in Pakistan, something like that. So we're allowed to do different color transformations in different space-time points, basically. So the kinetic terms, again, are no longer invariant. The old kinetic terms that we had, d mu phi, no longer invariant because of the x mu dependence in phi. Well, it's really the x mu dependence in the g of x, because phi of x goes to g of x times phi. So it's going to hit the x dependence in G. So now we're going to introduce a covariant derivative again. d mu phi is defined to this. This is the non-abelian covariant derivative. It's going to look quite similar to the abelian case. So we've introduced a couple of things here. So now we've introduced another A mu field, but now A mu of x is in the Lie algebra of G. Lambda is just some real parameter, is a gauge coupling constant. Okay, so what is this A mu of x? Well, it's in the Lie algebra of the group, so it's got to be some n by n anti-Hermitian matrix. Okay, so we have to come up with some potential transformation for this matrix field. It's really a matrix of fields. So we postulate for now that A mu of x goes to G times A mu G to the minus 1 over lambda d mu G G to the minus 1. In the case that A mu is proportional to the identity, or in fact isn't a matrix at all, this reduces to something very akin to the abelian case. So note that both terms on the right-hand side are in the Lie algebra of G. So, okay, we're going to show that now. So since A mu is in the Lie algebra of G, in equation 3.0, we showed that this first term was. And the second term is a bit more tricky, and we have to do a little bit of work now. So let's so to see the second term, to see that the second term is put G of t in the group as a curve. And then I'm going to call G dot again is this dg by dt. So this is the tangent matrix. At G of t. And G of t plus epsilon, where epsilon is an arbitrarily small infinitesimal parameter. This is, we can just Taylor expand this. Everything's smooth in Lie groups. And so we can Taylor expand to first order. Okay, let's write G, let's write this thing as some product in G. So writing G of t plus epsilon as a product, as a group product. So we set it equal to some h of epsilon times g of t, where, okay, h of epsilon is the identity matrix plus epsilon x plus order epsilon squared for some x of t in the Lie algebra. Okay, so this is equal to g of t plus epsilon times g of t to the minus 1. Which is equal to g of t plus epsilon g dot of t plus order epsilon squared g of t. This is just substituting in for g of t plus epsilon, sorry. So what this means is that x, okay, so x, oops, damn, x is equal to g dot of t, g of t to the minus 1, and it is in the Lie algebra. Okay, so we just did it for the time coordinate, but we could do it now, repeat it with time replaced by xi to see that d mu of g of x mu is in the Lie algebra of G. Okay, so I should have pointed out that this t here really means time. The x0th component. Okay, good. So, all right. So that means the second term, d mu g, is in the Lie algebra of G2. Okay, so how does the covariant derivative transform? Well, the covariant derivative, d mu of phi, is d mu minus lambda a mu of phi. Okay, so this transforms to d mu plus lambda g a mu g to the minus 1 minus sorry, I missed a factor of g here. Okay, minus d mu g. That's not g, it's g to the minus 1. Okay. Beg your pardon. Okay. So this is the way that it transforms. And so this is equal to, we just expand out the terms, d mu g times phi plus g d mu phi plus lambda g a mu phi minus d mu g phi. And of course, in the last term, the g to the minus 1 times g is just the identity matrix. So we see that the first and the last terms cancel, and we just end up with g times d mu phi. So just like in the abelian case, this covariant derivative is going to help us define a gauge invariant Lagrangian, and we'll see that next time.